Good morning, my dear friends. I hope you all are doing great. Today, my dear friends, we'll be looking at the relation between molar heat capacity at constant volume and molar heat capacity at constant pressure for an ideal gas. So let us start, my dear friends, our work. First of all, I will take on molar heat capacity at constant volume. So have a look here. Let's flip on. So our first terminology will be at constant value. What are the possible things? Let's draw. Let's take on one closed cylinder here. Okay. My dear friends, let me keep an ideal gas in this particular cylinder. Okay. So let us suppose we have here 1 mole of an ideal gas. Because I am talking about molar heat capacity, it will be related to 1 mole. Remember that. That's why I am taking 1 mole of an ideal gas. So what I am going to do, this thing is a piston. If this piston moves up and down, then there will be a change in volume. But I told you my topic is at constant volume, we have to check the molar heat capacity, my dear friends. So I will keep this piston as fixed. So I will take fixed piston. So when piston is fixed, you cannot move it. When the piston is not moving, the change in volume will be 0. When we do some process, have a look. Let me apply heat. Okay. Let us consider this wall as diathermic wall. So this wall is diathermic wall. Because you are supplying the heat Q, okay, to the system. Okay. When you supply heat Q to the system, so what will happen for this system? There will be a change in temperature. You can put a thermometer into it, and through thermometer you can calculate the change in temperature. But in case of molar heat capacity, if I am taking 1 mole of an ideal gas, then I have to apply heat. Once I apply the heat, I have to raise the temperature by 1 degree Celsius, my dear friends. So for this 1 mole of a gas, the increase in temperature should be 1 degree Celsius. That means here the temperature is increasing, we know that. So change is here positive, it's increasing. And we know that the increase should be by 1 Kelvin or by 1 degree. That we already know. Okay. So my dear friends, with the change in temperature, my dear friends, what will happen? The internal energy of the system, this system, will also increase. So when you are supplying heat to the system, and in system we have 1 mole of an ideal gas, there is an increase in temperature, and temperature increase is by 1 Kelvin. We call it as molar heat capacity at constant value. Why? Because this piston is fixed, it's not moving. There is no change in the value here. So my dear friends, we also know that at constant value, so delta V will be equal to 0, my dear friends. Correct? So when volume is constant, delta V is 0 for this particular process. So what I am going to do, can you tell me what will be the work? Work is equal to minus P external delta V. So delta V is 0, my dear friends. So I will be getting P external delta V is 0, so it's 0. So in this particular system, okay, while we are heating basically the gas, 1 mole of an ideal gas, so the piston is fixed, there is no change in the volume. So change in volume is basically 0 here. So work done will be also 0, my dear friends. So please remember that particular point. Now let us go further and understand a few more things right out here. Now you know that the heat is absorbed by the system. This heat is absorbed by the system at constant volume. So my dear friends, I will write down QV. What is the meaning of QV? It is the heat absorbed by system at constant volume. And when the heat is absorbed by the system, that is 1 mole of a gas at constant volume, it will increase the temperature by 1 degree Celsius and it will also change the internal energy of the system, my dear friends. So can I write down that the heat supplied to the system, or we can say the heat absorbed by the system from the surroundings, okay, will change the internal energy of the system. So internal energy of the system increases. So I will write down QV is equal to delta U. So that is my expression. The heat absorbed by the system. Who is the system? 1 mole of a gas is equal to the change in internal energy of the system. So internal energy of the system will change. What is that internal energy of the system? Internal energy of a gas will change. Yes? And you also know, let us write down this as expression number 1 or equation number 1. You are aware about the fact which I have told you previous time in previous class. You are aware about the fact that if I talk about QV, my dear friends, what is QV equal to? We have to understand. If I talk about here molar heat capacity, so let me write down here first of all molar heat capacity. Molar heat capacity will be given as CV at constant value. Molar heat capacity as CV at constant value. That is equal to Q upon N into delta T. That was my expression in previous class, my dear friends. Okay, I have derived this expression. Now I want this Q. This Q is the heat absorbed by the system at constant volume. So what will be the expression for the Q here? QV is equal to, look here, do we have here N, and let's multiply it by CV into delta T. This is the expression for the QV. Okay, so my dear friends, substituting the value of QV in equation 1 we get. You know the QV value here, my dear friends? Substitute the value of QV in equation first we get. So what are we going to get, my dear friends? We know that QV is equal to delta U. So in place of QV, I can write down NCV delta T. So in place of this, I can write down NCV delta T is equal to delta U, my dear friends. So let us call it as our equation number 2nd. Or even I can also write down here, my dear friends, now QV is equal to delta U is equal to NCV delta T. So this is the expression also I can mention. So please remember up to here. So make note of this. I will go further, my dear friends, and I will derive an expression for now molar heat capacity at constant pressure. And remember, this CV is nothing but molar heat capacity at constant value, and this CP is the molar heat capacity at constant pressure. So please remember up to here. So dear friends, we have derived this expression now. Delta U is equal to NCV delta T. Correct? So my dear friends, if this N is 1 mole of a gas, then obviously it is a molar heat capacity at constant value. We know this N is basically, so for 1 mole of an ideal gas, N is equal to 1. So we have delta U is equal to, in place of N, I will write down 1 now. So it will become CV delta T, my dear friends. So this is the expression, final expression. Because N value is equal to 1, because we are writing it for 1 mole of an ideal gas. So this N value will become 1, and finally I will get delta U is equal to CV delta T. Let's move further and talk about now molar heat capacity at constant pressure. So at constant pressure. So let us talk about molar heat capacity at constant pressure. Have a look, my dear friends, now here. Remember here it's a movable piston. That means piston is able to move up and down, correct? Let us take on, so when piston is able to move up and down, that means work will be done right out here. So in this case, work will be done. So this is heated, this gas is heated. So we have 1 mole of ideal gas with us. So let us heat it. When you are heating the gas, my dear friends, when you heat the gas, this is a movable piston. Piston will move. It will move upwards. You know that it will be the external pressure onto it, and through gas, when gas will get more kinetic energy because you are heating the gas. When you apply heat to the gas, gas will get more kinetic energy, and because of that more kinetic energy, it will hit the piston and piston will move upwards. That means there is a change in value. But remember, P external should be constant. Let us suppose you are taking atmospheric pressure as 1 atm, and that 1 atm pressure will always remain constant. So let's suppose you are carrying out this process at external pressure of 1 atmosphere. So this P external will be fixed, but P internal will keep on changing. How? Because you are supplying the heat. So when you supply the heat, kinetic energy of the gas will increase and P internal will increase, and then P internal will act against the P external and will make the piston to move upwards, and we know that this P external is fixed. That is, external pressure is constant. Okay. So my dear friends, here in this particular case, what are the things happening? I will tell you. You are supplying the heat Q. Okay. Heat Q is supplied here at constant pressure. So constant pressure basically here means you have kept P external constant. Let us suppose you have kept P external as 1 atmosphere. Only thing which is changing here is P internal. Basically, when you are supplying the heat, because of the heat, kinetic energy of the gas will increase and P internal will also increase. But remember, P external is constant. And let us keep that constant value as 1 atmosphere. Correct, my dear friends? Now you are supplying the heat to the system at constant external pressure, my dear friends. So when you are supplying the heat, that QP is equal to delta H, if you remember, change in enthalpy. Change in enthalpy of a system. And here also, when you are supplying the heat to the system, the temperature of the system will also increase here. There will be an increase in temperature of the system, my dear friends. Okay? Now, look here, QP is equal to delta H. We have derived it last time, if you remember. Or I can also write down QP is equal to delta H is equal to delta U plus P delta V. So that was the expression which I have derived in the previous classes, right? But I need just this expression here. QP is equal to delta H. That means heat absorbed at constant pressure is equal to the change in enthalpy of the system. Correct, my dear friends? So remember that particular point. So let us call it as equation number 4. So QP is equal to delta H. What is QP? Heat absorbed at constant pressure is equal to change in enthalpy of a system. Correct, my dear friends? Now let us go further, my dear friends. We know one more thing right out here, if you remember. That is QP I want to find out first of all. Okay? We are talking about molar heat capacity at constant pressure. Let me derive an equation for QP. Okay? So let us see here. I will write down here first of all CP, that is molar heat capacity at constant pressure. In previous class I have derived an expression that was QP upon N into delta T. This is the expression for CP, that is molar heat capacity at constant pressure. Now let us find out for QP. QP is equal to NCP delta T. So we know the value of QP here. So I will put the value of QP in this equation here. And this thing we have derived in previous classes, my dear friends. So let's have a look here, my dear friends. Now substitute the value of QP in equation 4. We get. So in place of QP, my dear friends, we have QP is equal to delta H. So in place of QP, I will write down NCP delta T. So here, I will write down NCP delta T. Okay, my dear friends. Let us call it as equation number 5. Or before calling it as equation number 5, let us do one thing. For 1 mole of an ideal gas, for 1 mole of an ideal gas, that is N is equal to 1, we have. What we have, my dear friends? N value is equal to 1. So we'll be having Cp delta T is equal to delta H, or we can say that this is the equation number, let us suppose 5. So now, my dear friends, in previous equation I found that delta U is equal to Cv delta T, and here I found that delta H is equal to Cp delta T. So let me mention it like this: delta H is equal to Cp delta T, and this C should be capital, my dear friends. Correct? So this is my expression. So I got the expression for delta U when the value was constant, change in internal energy, and I got the expression for the change in enthalpy when the pressure was constant, my dear friends. So now what I am going to do is that I will put both these values into an equation of enthalpy change, which we have also derived previous time, correct? So please make note of this, and I will go further after that. So dear friends, we have reached to this particular point where delta H is equal to Cp delta T. Look here, my dear friends, we know delta H is equal to delta U plus P del V. This expression we have already derived in the previous class. Yes or no? So now, my dear friends, what is the relationship of this expression with our delta H and delta U? Yes or no? So let us see, my dear friends. If you look at here P delta V, have a look. My dear friends, I can change this expression, this P delta V. Have a look here. How can we change this expression? We know that PV is equal to nRT. Yes, that's my expression. Let me call this equation as equation number 6, my dear friends. We know that when the external pressure is basically constant, at that time work is done. But if the value is constant, then no work is done. So if I write down here P delta V, this will represent the work done under constant pressure. Yes, I know. So my dear friends, there are many expressions of writing nRT. In previous one of the classes for gaseous reaction, you have derived P delta V is equal to delta N gaseous RT. But here in this question, my dear friends, we have only 1 mole of a gas. So number of moles are not changing here. Please try to understand. If I write down this expression, my dear friends, which I have derived in the previous classes, you will find out that I derived P delta V is equal to delta N RT. That was only possible when RT and P were constant. This was constant, constant, and the value was changing with respect to number of moles of a gas. But here, in this question, the number of moles of gas are fixed, they are 1. We have only 1 mole of an ideal gas here, so number of moles are not changing, so number of moles are constant. So my dear friends, this expression, what I have written here, I can write down here now, we have N, because we have here 1 mole of an ideal gas. So it is constant, or we can say its value is fixed. Let's come to the second point now here. What is that? R. R is basically the universal gas constant. But one factor will change. What is that? Temperature, my dear friends. How? Because you are supplying the heat to the system at constant volume and constant pressure. In both cases, the temperature of the system will increase, which you can check by using the thermometer, my dear friends. That means temperature is changing here, my dear friends. So T is not constant here, so I will write down here del T. So finally, my dear friends, my expression will be here. And number of moles are constant, so I can't write down delta N. R is also constant, correct? It's a universal gas constant, but temperature is changing. When we are heating the system at constant pressure, what happens? Temperature changes. Even at constant value also it is changing. So we can write down here delta T. So this is my expression for P delta V is equal to NR delta T. So now I will replace this value P delta V with this particular value NR delta T. And we know that we have here 1 mole, N is equal to 1. We are aware about the fact that number of moles of gas are 1. We have only 1 mole of ideal gas. So this expression will become P delta V is equal to R delta T, because we have only 1 mole of a gas which is constant. So now I can replace this expression. Yes? This is not required now, my dear friends. I hope you have understood. So let me go further. Substitute the value of P delta V in equation 6 we get. So we will have delta H is equal to delta U plus, in place of this P delta V, we know that P delta V is equal to R delta T. It's equal to R delta T. Actually it's equal to NR delta T, but N is 1 mole, so we are not writing it out. So R delta T we got here, my dear friends. Let's call it as equation number 7. Now we also know the value of delta H and delta U, my dear friends. We have already derived the value of enthalpy change and the value of internal energy change. Yes or no? We know these values. Already we have derived the value of enthalpy change, that's equal to Cp delta T, and delta U is equal to Cv delta T. So these values already we have derived. So substitute the values of delta H and delta U in equation 7. Sir? Substitute the value or values of delta H and delta U in equation number 7. We get. So my dear friends, what's my equation number 7? What is in place of delta H? What can I write down? I will write down Cp. So in place of this, I will write down Cp delta T. Cp delta T. And in place of delta U, I will write down Cv delta T. Cv delta T plus RT. R delta T. So my dear friends, now let us simplify it. Cp delta T is equal to Cv plus R, and let us take this delta T as common. Correct? So this and this will cancel, my dear friends, and finally you will have Cp is equal to Cp plus R. Cp is equal to Cv plus R, and finally Cp minus Cv is equal to R, my dear friends. And this is the expression for 1 mole of an ideal gas, my dear friends. So finally I derived a relationship between Cv and Cp for an ideal gas. So we have taken just 1 mole of an ideal gas, my dear friends. If you take 2 moles of an ideal gas, then this N factor will be 2. And 2 is also constant. If you take 10 moles also, that's also constant, but you should not change the number of moles. You should, if you take 1000 moles also, but keep it constant. But it will not become a molar heat capacity at that particular time. Molar heat capacity is only taken for 1 mole of a particular substance. Remember that thing. So you have here Cp minus Cv is equal to R. That is molar heat capacity at constant pressure minus molar heat capacity at constant value is equal to a constant, and that constant is universal gas constant, my dear friends. Please make note of this. So dear friends, let's talk about now the measurement of internal energy change and enthalpy change. So for understanding the first point here, the measurement of delta U. So first of all, we'll take on measurement of delta U. Everybody is aware that delta U is the change in internal energy. So in order to understand this delta U, we have to take the bomb calorimeter. So what is this bomb calorimeter all about? Let's have a look. So my dear friends, in this particular chamber or in this particular closed chamber, I have taken water here. That is water at 25 degrees Celsius, my dear friends. And these walls actually, my dear friends, they are adiabatic walls, or we also call it as insulating jacket. So these walls are adiabatic. That means through these walls heat cannot come out. That means heat cannot come out here. And inside this particular chamber you have water, and water is at 25 degrees Celsius. And inside the water you have put the thermometer to check the change in temperature. How temperature is going to change, my dear friends? Let us understand that term first. In this particular chamber, let us call this chamber as steel bomb. This chamber is known as steel bomb. This chamber I am talking about, my dear friends. That means the heat can transfer from this chamber into the water, or heat can transfer from water into the chamber. That means this wall is made up of steel, and steel will let the heat flow out here. Yes, I know. So this wall, the steel bomb, is basically the wall of the steel bomb is diathermic wall. So what is happening in the bomb calorimeter, my dear friends? We are taking a fuel here, or a combustible substance. You can look here, my dear friends. We are taking a sample, and this is our sample. You can have a look here. This is our sample. Let me mention it. So can you see right out here? This is our sample. And what is our sample, my dear friends? A combustible substance. Means a substance which can be burned, and we can call it as fuel also. And let us suppose we are burning graphite here. Let us suppose this is graphite here. This is graphite. So we are burning the graphite inside. So my dear friends, in order to burn the graphite, my dear friends, you need oxygen. Yes, I know, because oxygen is required for combustion. So you are forcing the oxygen inside. So oxygen gas is coming inside here, my dear friends. As it travels inside, and this oxygen gas is under high pressure. Have a look here. So through this opening you are making the oxygen gas to enter inside. What is present inside, my dear friends? Sample. Which sample is there? Fuel. We call it as, let us suppose, graphite. You can use any fuel, but I am using graphite here, correct? So my dear friends, now oxygen has been put inside. In presence of oxygen at high pressure, this graphite has to burn. So oxygen will make the graphite to burn. But remember, it requires some ignition. Some amount of heat is required for burning the graphite. Yes or no, my dear friends? This is your graphite here, and this is the oxygen here. So two things are present. What are those two things, my dear friends? Graphite is present. Graphite is nothing but carbon. And oxygen is also present. Correct? Now, will it burn or will not burn? It won't burn, my dear friends. It needs some ignition. Some amount of heat is required at the beginning. Once you burn it, then the combustion will keep on going, keep on going. So, what is the way to burn this particular graphite in presence of oxygen? Now, have a look here, my dear friends. You can have a look here. This is a firing rod. We call it as a firing rod. These two rods are connected to a battery. So you can take these two rods, this one and this one, and they are here put in touch with the fuel, and fuel is nothing but it's your graphite. So my dear friends, these two rods are connected to a battery, power source. So this power source will provide the current, and this current will pass through these rods, okay? Then these rods will be made to give electric spark. When you touch these two rods will give the electric spark to the fuel. Fuel is graphite, and graphite will burn in presence of oxygen when you are giving the electric spark. And we call these wires as ignition wires. And these rods can be also called as firing rods. They can be also called as firing rods. Now the graphite has burnt. What you will get? You will get carbon dioxide, and heat energy will be also released. So in this process, heat energy is produced. When this heat energy is produced in this process, now what is going to happen? This substance is graphite. It is burning in presence of oxygen, and some little energy is provided by the battery. Battery is providing the energy for burning. So once it starts burning, then it does not need any kind of electric spark after that. Because at homes, the gas, when you switch on the gas, you are giving a little spark of energy by using the lighter. Once you burn the gas, my dear friends, after that it does not require your spark and all those things. So that little amount of energy which you have provided to the LPG gas at home, okay, that will burn the gas in presence of oxygen. Yes? But that little spark is required or not at the beginning. In the same way, graphite will burn in presence of oxygen to give carbon dioxide. But at the beginning of the reaction, you have to give some electric spark to start the reaction. So electric spark is here used to start the reaction. Once it starts, it will continue by itself. Remember that particular point. So we are using the battery and we are giving the spark and burning the graphite here. So now, during this reaction, chemical reaction, heat energy is produced. So this heat energy, you know this wall is basically it's a bomb calorimeter. Basically this entire thing is bomb calorimeter. This entire device is a bomb calorimeter, my dear friends. And this is a steel bomb. This area is only a steel bomb. The entire thing is bomb calorimeter. So this steel bomb has the walls which are diathermic. So that means during combustion of this particular graphite, what will happen? The heat will come out, my dear friends. So heat will come out of the steel bomb. So heat has come out. So this steel bomb will release the heat because combustion of gas is taking place. So now, my dear friends, the heat is flowing from the steel bomb into the water. And this is the water right out here. Now heat cannot flow from water to outside because these walls are adiabatic. So graphite is burning here in presence of oxygen. So it produces heat. Heat energy is produced. That heat goes from steel bomb, this is the steel bomb, into the water. When heat travels into the water, my dear friends, we have a thermometer in the water. Let us suppose the temperature at the beginning was 25 degrees Celsius. Let us suppose the initial temperature was with us 25 degrees. So initial temperature was 25 degrees Celsius. And once the heat is released by the steel bomb into the water, we can measure the temperature reading by thermometer. Thermometer is here. So let us suppose the final temperature is now 26 degrees Celsius. Let us suppose 26 degrees Celsius. Now what is the change in temperature, my dear friends? 26 minus 25, how much is that? 1. So by 1 degree Celsius the temperature of the water has basically changed. So now what is my point? This entire system is basically fixed. There is no chance of the work here. Work cannot be done here because it's a completely rigid system, a fixed system, my dear friends. And remember, this bomb calorimeter is basically an isolated system because no heat can come out. Heat can come out from steel bomb into the water, but from water, heat cannot come into the surroundings because these walls are adiabatic, my dear friends. So what is my point here? There is a change in temperature here, my dear friends. Now, during this particular, reaction, what was happening? The heat energy was basically, lost, and it was moving from the steel bomb into the water, my dear friends. Now, so dear friends, the temperature of water has increased by 1 degree Celsius, and we know that internal energy of water will also depend upon what? Temperature. So that means here the delta U will also increase here. Temperature of water has increased and the internal energy of the water will also increase. And you know, my dear friends, this system is basically a closed system and there is no possibility of a change in volume here. So obviously the work done will be 0 right out here. Okay. As bomb calorimeter is a closed, let's write down, it's an isolated system. Having fixed value. So delta V is equal to 0. When delta V is equal to 0, W is also equal to 0. When volume is not changing, P delta V will be also 0. So work done is also 0. Now I am talking about measurement of delta U. So obviously that will be given by an equation called as QV, because heat will be here absorbed by the water. Let us consider, because water is the part of the calorimeter, my dear friends. So obviously the heat absorbed by the water is equal to the change in internal energy, my dear friends. When water absorbs the heat, what happens? The temperature will change and the internal energy will also change, because internal energy depends on temperature. That means finally I will write down QV is equal to delta U, my dear friends. Yes? So here I will tell you that the heat absorbed by the water at constant volume is equal to, come on, the change in internal energy of the calorimeter, my dear friends. So let's have a look here. Even in terms of calorimeter also we can write down here. You can also write down heat absorbed by calorimeter. So try to understand, this calorimeter is basically the entire system is the calorimeter. Okay? And here who is absorbing the heat? You should remember that. When I wrote heat is absorbed by calorimeter, understand the heat is actually absorbed by the water. So with this calorimeter you should remember that which part of the calorimeter is absorbing the heat. So it's a water which is absorbing the heat. Okay? Heat absorbed by calorimeter at constant volume is equal to change in internal energy of the system, or we can say it's equal to the change in internal energy of the system here, or of the calorimeter. So heat absorbed by calorimeter at constant volume is equal to change in internal energy of the calorimeter, my dear friends. So when this steel bomb will release the heat, then
water will absorb the heat, my dear friends, and temperature of water will increase. Internal energy of water will also increase. So finally I will write down QV is equal to delta U, that is heat absorbed by the calorimeter at constant value is equal to change in internal energy of the calorimeter. And remember, this calorimeter basically signifies here the entire system. And in that entire system, who is absorbing the heat? You should remember that. That is water. So remember, in place of calorimeter, you can replace it by water also. Try to understand. Calorimeter means entire system. But water basically means that particular substance who is absorbing the heat. So internal energy of water will also change. So dear friends, now you've got to know that QV is equal to delta U, change in internal energy. Let's call it as equation 1. And you know the value of QV. If I relate it to the heat capacity, my dear friends, remember QV is equal to CV delta T. When I am writing this particular term, you understand that this is the heat capacity at constant value. If I write down QV is equal to mCV delta T, then it becomes molar heat capacity. If I write down mCV delta T, then it becomes specific heat capacity, my dear friends. Molar heat capacity is specific. But if I don't mention M and M, I will write down directly CV delta T, it becomes heat capacity. Please remember that. So, my dear friends, let's go further. Let us substitute the value of QV in this equation. So, substitute the value of QV in equation 1. We get. So we will get here, in place of QV, we will write down CV delta T is equal to delta U. So that is my final expression here, my dear friends. So how can you calculate the change in internal energy of a particular substance or particular calorimeter? You are calculating the internal change of the calorimeter. Okay, that's equal to CV into delta T. Or you can write down you are calculating the internal energy change of water which is present in calorimeter, right? That's equal to CV delta T. That is heat capacity at constant value into change in temperature, that is rise in temperature. So this is the final expression of the measurement of delta U, my dear friends. Now you will be thinking, if this is the expression, what about the combustible substance? This combustible substance is basically releasing the heat. Water is basically absorbing the heat. So this expression will be for water especially. What about the substance which is losing the heat? Who is losing the heat, man? I am burning the graphite here. That guy is losing the heat. Yes or no? So when graphite is losing the heat, what will be the expression for the graphite or for a combustible substance, my dear friends? For a combustible substance, what will be this expression all about, my dear friends? It will be delta U is equal to minus CV delta T. So this expression will be for the combustible substance. And this can be related to the calorimeter. So it's with respect to water and it's with respect to combustible substance. So combustible substance will have a minus value because this combustible substance will lose the heat. So I will take it as minus. And the water is absorbing the heat. So I will take it as plus. Yes. And for calorimeter, if we talk about now, usually in this calorimeter with respect to combustible substance, in this bomb calorimeter I am talking about, with respect to combustible substance, delta U is equal to minus CV delta T. And in this bomb calorimeter, with respect to water, delta U is equal to plus CV delta T. Because this guy is losing the heat and this guy is absorbing the heat. Remember that particular thing. I hope you have understood, my dear friends. Please make note of this. So dear friends, let us talk about the measurement of delta H, and this is taken at constant pressure, that's atmospheric pressure. You know that, let us suppose in this cup which is having a diathermic wall, means it can transfer the heat, and this is, let us suppose, the water here. Let's suppose we have water here, water at 25 degrees Celsius. So my dear friends, in this particular small cup, okay, there is a reaction mixture. Some reaction is taking place in this particular cup. Okay. So what is happening? If that reaction is exothermic, then the heat energy will be transferred outside. Yes or no? Let us suppose in this cup I am talking about, a reaction mixture is there, and let us suppose exothermic reaction is taking place. Exothermic reaction. So in exothermic reaction, everybody knows that heat is lost. So heat will be lost from this particular system here. So this reaction mixture will lose the heat, and heat will be absorbed by the water. So water will absorb the heat. So when the heat is absorbed by the water, the temperature change can be calculated by the thermometer, my dear friends. So obviously, let us suppose the reaction is exothermic reaction. Then what will happen, my dear friends? Heat is given out, okay, by this small cup. If you see this small cup, let's call it as a small cup here. So heat is given out by the reaction, okay, which travels from small cup into the water. So when it travels from small cup into the water, the temperature rise, okay, in water will be calculated by thermometer. So now you are aware about this particular thing now. The heat is lost by this reaction which is absorbed by water. So temperature of water will increase. And we know that this entire process is taking place at constant pressure. So that means the heat will be written as QP. That is the heat absorbed by the water. Yes, will be equal to. And you know that in previous classes I have also told you that QP is equal to delta H, the change in enthalpy, my dear friends. And remember that QP in terms of heat capacity can be related to as Cp delta T, and this C stands for your heat capacity. So my dear friends, this will be the expression for us, and remember this is with respect to water. So that means, my dear friends, when the reaction takes place in this system, let us suppose that reaction is exothermic, heat is lost, heat comes out, because this wall is basically diathermic, water will absorb the heat, the temperature of water will rise, it will increase. So obviously when temperature of water increases, my dear friends, what will happen? We can easily calculate the heat absorbed by the water at constant pressure. That will be equal to the change in enthalpy, okay, and that's equal to Cp delta T, my dear friends. And remember one important thing here, that is, if you talk about QP in terms of this reaction now, or in this terms of this system where the reaction takes place, then obviously this term will become minus. So this is with respect to water. If I talk about this thing with respect to reaction mixture, let us suppose delta H is equal to Cp delta T. This is with respect to water. Water is absorbing the heat, okay. Now if I talk about delta H is equal to minus Cp delta T, this will be with respect to reaction mixture. Because reaction mixture is losing the heat. When reaction takes place, heat is lost. Because I mentioned that the reaction is exothermic, my dear friends. Now if the reaction is endothermic, then heat will be absorbed. That means water will lose the heat, or what heat will flow from water into the reaction mixture if it is endothermic. So remember these two terms which I have already told you, that delta H is positive for endothermic reaction, and it is negative for the exothermic reaction. I hope you have understood. That's all for today. Take care of yourself, my dear friends. Have a great time.